thank you for the introduction. And I also would like to thank Francesco for inviting me. I gave everything to come here. So this talk is about joint work with Claudio Loza Isenrich and Charles Wu about homological finiteness properties of simple groups. So before giving the talk, I was not sure what kind of audience I have to expect, and now I see like the first slides are way too elementary. So let's just make it very short. So group type Fn, it's like this 3G CW complex with finite n skeleton mod, the group action. And F infinity, it's like if it is Fn for every n. Okay, so typically groups arising in H times they are finally presented are typically also F infinity, free groups, polycyclic groups, hyperbolic groups, out Fn, SLM, and also like the infinite dimensional groups also tend to have this property. Okay, so in this talk it will be more going to this type of groups, and yeah. Why are finiteness properties interesting? As you know, F1 equivalent to finally generated, F2 equivalent to finally presented. Okay, I think now we're convinced that these are interesting group invariants. So the first question that arises is, can one actually find for every n a group of type Fn but not Fn plus 1? So can one separate groups by these properties? This, like for the first n, this is almost 100 years old, the result that there are uncountable many groups. So in particular, finally generated, not finally presented groups exist. The first infinite series of groups separated by finiteness properties are provided by Beery and Stallings. And until today's state, like the prototype of groups that are separated by finiteness properties. And by prototype, I mean that there is some natural ambient group, in this case, product of non-abelian free groups, and there is a homomorphism to the infinite cyclic group, and the kernel of this homomorphism has like Fn, but not Fn minus 1, but not Fn. So often the point is that the geometry associated to this group is contractible, but if you consider only the slice of level 0 inside this geometry, it appears to have the geometry that has this property. Okay. Yeah, since then, all kinds of examples of groups appeared that have this separated by finiteness properties. Solvable groups were provided by Arbus and Brown. Recently, examples were found within hyperbolic groups by Claudio and Pierre Pai. Another interesting result was provided by Skipper, Witzel, and Zaremsky. They found simple groups separated by finiteness properties. So meanwhile, as we see, there are plenty of examples of Fn, but not Fn plus 1. So is it really exotic still? Okay, decide yourself. But what is definitely still exotic if we replace Fn by the homological finiteness properties. So here we have a commutative unitary ring R. Yeah, and the group is of type Fpnr if R, regarded as a trivial Rg module, has a resolution by projective Rg modules that are finally generated up to degree n. And again, F infinity means Fp infinity R means Fpnr for every n. Okay. Yeah, there is an obvious connection to Fn. Fn implies Fpnr for every R. And also there are a few other connections. For F1, it is equivalent to Fp1R for every non-trivial R. There's a not so obvious connection in the case of finally presented groups. Then it turns out that Fpnz is equivalent to Fpn. And the opposite direction was open for a while. So groups, by Bisfina and Brady, there was a breakthrough that the opposite direction does not hold. However, there's still not many examples that give negative answer to this question. So the goal of this talk is to provide a corresponding result for the Skipper-Witzel-Zaremsky result, but like for that answer this question negative as well in the class of simple groups. Okay. Okay, I think this we can skip as well. Yeah, but still we recall the Bisfina-Brady result because we will actually need it. Yeah, we start with the graph gamma. We consider the kind of morphism from the right-angled arting group associated to gamma that sends every generator to 1. And then the kernel of this morphism will have finiteness properties completely determined by the topology of the flag complex of gamma. If it's n-1 connected, the kernel is Fn. If it is homological n-1 connected over R, then it is Fpnr. Then if it's like contractible, it's F infinity. In fact, it has finite. In fact, it is type F. But for this talk, everything nothing will be finite dimension and nothing will have finite homological dimension. We only consider F infinity. F infinity. Yeah. Okay. So as an application, they provided a group of type Fp infinity over Z, but it is not finally presented. In fact, Fp over Z. And similarly, groups separated by homological finiteness properties that are not finally presented. So this is one of the few occasions where not finally presented makes something more interesting. Okay, so as usual, we will call this kernel Spesvina-Brady groups, denoted by BB gamma. So, and we will need the main result stated like this. And also we will need just one further fact of Spesvina-Brady groups, namely that they are linear over Z, in fact. This is also well known, easily to see, namely rags embed into right-angled Coxeter groups by like octahedralization of this graph. Coxeter groups, in turn, if they are right-angled, their Coxeter diagram induces integral cosine matrices. So the standard representation of Coxeter groups is, in fact, not only has image in GL and R, but in GL and Z. Okay, so this fact we remind. Yeah, until then there are not too many results of groups with not too many results of groups with exotic homological finiteness properties. By exotic, I mean here not finally presented, but of type Fp2. So Leary, but there are plenty of them. There are not many examples, but somehow there are still plenty of them, since every countable group embeds into such a group. This is a result of Ian Leary. Another interesting result is goes into the direction of finding exotic examples with exotic homological finiteness properties. Is by Rob Coppola. In hyperbolic groups, he found an example, not F2 but Fp of Fp2. And now, yeah, our contribution to this is that there are also simple groups with Spesvina-Brady type finiteness properties. So exactly, like literally the same result holds, but for simple instead of kernels of right-angled Latin groups. So we start with a finite graph gamma. We associate to it a simple group G gamma, and yeah, for a given ring R, G gamma will be of type Fn. If the flag complex is n-1 connected, and so on. This is literally the same. But here F infinity, I guess, cannot be replaced by F. And unfortunately, this is, I can also not tell you this as a feature, since our group will have torsion. Also virtually it will have torsion. Okay. Yeah, and the applications are the same. So once we have groups associated to graphs and finiteness properties are determined by connectivity properties of the flag complex, we deduce in the same way as Spesvina-Brady that there exist simple groups that are not finally presented, but Fp infinity over Z, and not finally presented and separated by Fpn. Interestingly, very recently, so this kind of results seem to be in the air this currently. I got several emails asking this question, and in the TDLC world, in the non-discrete, totally disconnected, locally compact group, a few weeks ago, the corresponding result appeared by Bonn and Giersbach. They showed that there are non-discrete, totally disconnected groups that are not compactly presented. So it's like the analog of finally presented in the group, in the class of TDLC groups, but they are still of type Fp. Abstractly simple. So in this, I asked, it's in fact abstractly simple. Yeah, but we read this paper, and also we showed some our results. It seems like neither their results techniques are able to provide discrete examples, nor do our techniques. So we don't see how they give rise to non-discrete examples. Okay. Yeah, the main result that I stated is deduced from another result. It's almost a direct consequence from the following theorem. We start with a finally generated subgroup that is linear over Q. And then the claim is that there exists a group, a simple group, that has the same finiteness properties as H. Recall that Spinor-Brady groups are linear over Z, so in particular, H can be chosen as such a group. H is a subgroup, and G admits H is a quasi-retract. So this is actually the way we get the negative finiteness properties. Yeah, as I remarked, Q, we could replace this by algebraic closure. There's an easy trick of embedding finally generated subgroups of GL and Q into GL and Q algebraic closure into GLMQ for M appropriate multiple of N. But the technique, it does not work if we allow if you include transcendental elements. This is a pity, since this would have some interesting applications. Yeah, and that's why we ask whether we can replace Q by an arbitrary field. The characteristic is not the problem is like transcendental elements. And there are interesting groups that have linear representations but use transcendental elements like braid groups. Okay, yeah, and then as an analog of Leary's result, we propose the question of whether countable groups can be embedded into simple groups of type FP to Z. Now that there are simple groups of type FP to Z but not finally presented, it might make sense to ask. Okay, so how do our groups arise? So first we have to fix, so they are almost acting on the tree. And first, let us recall what kind of trees we consider. We consider rooted trees. For this, we fix an alphabet with at least 2 letters. We consider the free monoid over this alphabet, and consider the calligraph of the free monoid with respect to the basis x. Just the calligraph. And the purpose of like this specific alphabet is that we have a natural order on the leaves, on the vertices. Okay, out TD will denote the group of all automorphisms of the rooted tree. And by this, in particular, these automorphisms, they fix the root. And as a consequence, they fix like words of a given length, since they are precisely described as words of a given distance to the root. Since out TD fixes the root, it leaves invariant the sets xdn. So we have natural homomorphisms from the automorphism group of the rooted tree to like the symmetric group of xdn. In the case n equals 1, this simply gives us an element in the symmetric group SD. So let's call it rho f. On the other hand, the symmetric group admits a natural action on a rooted tree by just permuting the trees hanging below the first level vertices, like rigidly permutes these trees. And from now on, we will just identify this symmetric group with a subgroup of the rooted tree that rigidly permutes these groups. Okay, right. This was essentially what this notation says. This kind of automorphisms will be called rooted. It looks like this. We have like this permutation. We just permute these trees according to this permutation. So, and apart from the rooted ones, we need another type of tree automorphisms. These are given by as elements of the direct sum of the whole automorphism groups indexed by the alphabet. And it acts on the tree in the following way. If we have a tuple gx inside this direct sum, and we have some arbitrary word, so an arbitrary vertex, it starts with some letter. And then what this tuple does is it leaves the first letter as it is, and applies gy to the remaining word. So you have like the tree, and below these level 1 vertices, the GIs are hanging below. So the point is now with the rooted automorphisms and the direct sum automorphisms, we can decompose every tree automorphism as a product of first applying the direct sum and afterwards applying the rooted automorphism associated to F. And in fact, not only that there is this unique decomposition, the decomposition itself is an isomorphism from the tree automorphism into the Rees product of the symmetric group and the automorphism group of the tree. Yeah, Rees product, okay, one has to be careful actually, it is the permutational Rees product. So the symmetric group acts on this direct sum by permuting the coordinates. Okay, yeah, if one has this decomposition, yeah, if one applies this to an arbitrary word starting with x, what happens is that one applies the rooted part to x, which is just applying f to x, and fx to the remaining part. Okay, we need a slight generalization of this fx things. This slight generalization is given by the states of a tree automorphism. Given as follows: we have a rooted, we have f element of out Td, and we give a vertex u, and then we can associate to it a tree automorphism fu, and this is implicitly defined by the following equation. Whenever we see a word of the form uv, so u is fixed, v is variable, then what comes out is the first thing is completely determined by f, and so this is not a property, this is like always the case, and the second part is then given by fu v. This is a simple consequence of the fact that f is preserves the tree structure. Okay, these are the states. Call it the state of f at u. And with these states, we can now define the notion of self-similarity. So this is essentially the only ingredients that we need to define the Röver-Nekrashevich groups, which will be the groups from our main theorem. So generally, we can define a subset of the whole automorphism group of the tree to be self-similar if it has the property that whenever we have an element of the set, the states will lie in the set again. All of its states will lie in the set again. And now in the case where S is a group, we have the definition of self-similar group. So now, apparently, in the literature, there is a bit confusion with self-similarity and related notions. So let's recall related notions, first because they will appear, and second because of apparently there's a bit of confusion. First of all, there is a notion of automata groups, which is slightly more restrictive than self-similarity, although it is hard to find examples that are automata group that are self-similar but not automata groups. Automata group means that there is a finite generating set of G that is self-similar as a set. Yeah, one can, yeah. And yeah, one abstraction is that for automata groups that they have solvable word problem, while self-similar groups by a recent result of Bartholdi and Mitrofanov do not have solvable word problem in general. Okay, then there is a notion of finite state, which means that for a given element of the automorphism group, its set of states is finite. And similarly, a group is finite state if all of its elements are finite state. So now, if a group is an automata group, it is self-similar and all of its elements are finite state. But neither do finite groups that are finite states necessarily be automata groups, nor the other way around. But if one combines finite states and self-similarity, then this is exactly what automata groups is, as an easy exercise. But what we will need is that for checking self-similarity, this U can actually be replaced by the first level vertices. The point is that the state of a state is a state, so one can do like inductively show that from this it follows that one can take arbitrary U as vertices here. Okay, it's a very basic example. Okay, let's still give it. So we consider the adding machine, sometimes called the odometer. So it is defined implicitly by this equation. So we have a binary tree. The alphabet is 0, 1. And the automorphism that we consider is like given by this equation, it is a recursive definition. But still, this makes sense. So let me show you how this definition gives rise to a tree automorphism. So let's say we want to apply it to the word with 4 letters, 0, 0, 0, 0. Then what we do is we split A into its rooted part. So the rooted part is just transposition of 0 and 1, and like the direct sum part. So then we apply sigma to the first letter, and we decide by looking at the word what is the first letter. It is 0. 0 is a smaller one. We apply the left automorphism. So identity to the rest. So we get 1, 0, 0, 0. And then if we repeat the process, we see that this thing actually makes sense to call it the adding machine. It's binary adding. Yeah, it is obviously finite state, since all of the states of A will be either identity or A. The generating set, the set identity A is self-similar. So the subgroup generated by the set is an automata group. And in particular, it is self-similar. Okay. In general, it is not so easy to decide whether a given group is self-similar. And the reason is that on the one hand, there are barely any obstructions. Not even the word problem is an obstruction. The residual finiteness is an obstruction. But apart from like the obvious obstruction of residual finiteness, there are barely any obstructions known. But on the other hand, there are also few constructions of those. Actually, we will see all of them. Yeah, very limited. One interesting result that goes into like understanding what groups are self-similar was provided by Kapovich. He considered irreducible lattices in semi-simple algebraic Lie groups, and he showed that being self-similar can be characterized by being arithmetic. Although it's still unclear whether the examples that he has are also automata groups. So the self-similar representations that he found is not, is what he writes, but still there might be another one.
Say anything about obstruction. You said it's very hard to obstruct self-similarity, but there are a lot of lattices there that he's saying are not self-similar. Can you say what?
Okay. Okay, there is an obstruction, namely if the abstract commensurator group coincides with the automorphism group, then the game is over. It cannot be self-similar. Then, of course, it has to act not only on the rooted tree, but on a rooted tree that is has bounded width. So equivalently, there exists a finite set of simple groups, such let's call it F, such that the group is residually poly F. So if this is satisfied and like the yes, there is a finite exactly yeah. This is just that the group can act on the tree with bounded width. Yeah, and apart from this, I don't know examples, but there have to be many, since there are only countably many self-similar groups. Self-similar groups are, one can define them in terms of certain automata, but there are uncountably many of those. Yeah. But the non-arithmetic lattice is also. I'm not an expert in this, but didn't they tend to be also not linear? Okay, I see. Linear. I was thinking about linear over Q. Okay, it might be that they give. Actually, we will see further examples, but that are what could a priori be self-similar, but are not. Out Fn is an example. Well, okay. Yeah, Baum's-like solitary groups are automata groups. Grigorchuk's group is an automata group, if you're interested in this. But these are kind of automata groups that are defined to be automata groups. So similar, one can write down presentations and ask yourself what you have done, and this the same can be done for self-similar groups and automata groups. One can draw an automata, so there are plenty of them, and then ask yourself what you have done. Sometimes some interesting group comes out of it. Yeah, out Fn is not self-similar, and the reason is that, okay, they did not formulate it that way, but it is almost a direct consequence, since the abstract commensurator is coincides with the automorphism group of out Fn. So, okay, the examples that we need today are of the form affine groups over some ring R. So we consider like the affine group to have this general linear part, and Rn is a translation part. So it is known, actually was observed by several people in various contexts and also in different language, that the affine group Fnz is self-similar. We need a slight generalization of that. So we try to generalize it. And to do so, we consider the p-adic integers. Inside the p-adic integers, there are lots of rings. So the rings that we are interested in are what we call rigid. So actually, I guess there is already a commutative algebra definition of this what we call rigid, but we didn't find it. So a ring in that subring of Zp is rigid if an element in Zp lies in R if and only if p times x lies in R. Or in other words, you consider the ideal generated by p in R, it is the same as the ideal generated by inside Zp and then intersection with R. Okay. Yeah, and the example that we need of a rigid ring is Z1 over n, where p does not divide n, right? N is invertible in Zp since p does not divide n. And then it's an easy exercise to show that it is in fact rigid in this way. Okay. Yeah, and what we want to show is that whenever we have such a rigid ring and an arbitrary subgroup of the general linear group over R, then it turns out that after adding the affine part to Q, then it becomes self-similar. So, and this is not such a deep result. Nice, it's an easy observation actually. So in order to see this, we first realize the whole affine group over Zp, so an uncountable group, as a self-similar subgroup of the automorphism group, and then show that after we have understood this action, restrict the action to the subgroup and see how it's still self-similar. Okay, to this end, we first have to define the tree on which the group acts. So we fix capital N and small n, and the prime that does not divide capital N. The alphabet that we are looking at is like the n-dimensional p vector space of a prime field Fp. And yeah, so the tree that associated to this alphabet we call Tpn. And the boundary of this tree, of course, corresponds to the infinite words over this alphabet. And the infinite words in turn, they correspond to Zp to the n, just in the, via the sum notation. We have the sequence xn over this alphabet, and then we regard it as the coefficients of pi into the series notation of Zp. Oh, it should, yeah, exactly. Okay. Okay, this is just what was written before. So now we have the natural action of the affine group corresponding to Zp. It acts on Zpn. And this affine group, it translates then to an action of, yeah, it's just a subgroup of the tree automorphism of Tpn. So, and from now on, we regard it just as a subgroup of the tree automorphism group. Okay, so the lemma that I just told you, that after adding the affine part, it gets self-similar, it is a direct consequence of this lemma. So the point is that if we consider some affine transformation given by some linear part and some so the affine translation part, and then after we consider the state of this element at some letter x, then it turns out to be of this form. So the linear part stays exactly the same, but the affine part might change. But still, it will lie in R to the n under the assumption that the ring is rigid. So this is the only place where we need it. So let's start. We consider an element of the alphabet, and we consider some arbitrary element in zp to the n. Now we add them, so we get a general element that lies in zp to the n. So recall that this is just the boundary of the tree. So now if we let this affine transformation G act on X, whatever comes out of it, it will again have the form X prime PB prime, where X is an element of the alphabet and B prime is something. So then if we then calculate what happens if we apply G to U, then we see that the level 1 part is X prime, and the remaining part is given by applying A, comma B prime to W. So if we translate it back like to the tree language, this tells us that the state of G at X is simply the affine transformation given by A, B prime. So okay, and now after we like rewrite this equation here, we get like PB prime is this here, and X prime and X, they are integers. I mean, they are represented by finite sums, and in the sum notation, finite sums are just integers, ordinary integers. And B was by definition tuples of integers, and B was by definition an element of R to the n. So on the one hand, we have an element of R to the n, but on the other hand, we have a P multiple of B prime. So it is lies in the ideal span by P in ZPn. And now definition of rigidity tells us that this is exactly the P times R to the n. So as a conclusion, B prime indeed lies in R to the n. This is all that we need. Like now the B prime, now that it lies in R to the n, everything is done. So again, like this was the lemma, and this is the conclusion that I told you. So if for self-similarity, what we have, the only thing that we have to check is that this lies in the group itself. But we started with an element of GL and R, and if this element is in Q, then afterwards it still lies in Q. And after B prime replaces by B replaces by B prime, it still lies in R to the n. So everything is done. Okay, now we have the self-similar groups. What can we do with them? And at this point, it might make sense to ask. So whether some similar trick might be able to embed arbitrary finitely generated linear groups into self-similar groups. So embedding things into self-similar groups, there's even less obstructions now. So for example, here this group is self-similar, but after we forget about the Rn part, there is no reason to believe it is self-similar, and it definitely will not be the case in general. Yeah, but embedding is much easier. So maybe if this is true, then I claim one could prove Boole-Higman for linear groups. Okay, so where do our groups come from? We have now the self-similar ingredient. Now the remaining ingredient is like the Thompson ingredient. And for this, again, now let's switch back to the tree that we worked at the beginning. The alphabet is 1 to D. The Cantor set now we will denote by CD. And again, like it's a set of infinite words, and it's identified with the boundary of the tree. Like, to define this Thompson types groups, we will embed like the automorphism group into the homomorphism group of the boundary. It's clearly there's a canonical embedding. So what we need is some special subsets of this boundary, namely cones of, namely the boundaries of subtrees hanging below a given vertex. This is what we call a cone. So if we have some vertex u, just some vertex, then we consider all other vertices or infinite sequence that start with u. So here we have 3, 1, this is our vertex, and every infinite sequence that starts with this is a CD u, in this case CD 3, 1. Okay. So the last ingredient that we need, like to define Röver-Nekrashevich groups, is complete subtrees. So by complete, we mean that, yeah, first of all, it is finite. Second, it contains a root. And third, this is where the name comes from, whenever some vertex contains some descendant, it contains all of the descendants. This complete subtree. Okay. Yeah, and here finally we get to the point where it is an advantage of fixing the specific alphabet 1 to D, since now we have a natural enumeration of the leaves of the complete subtrees. Since now we have to define almost automorphisms, we first need to fix two complete subtrees of TD. They must have the same number of leaves, say n leaves. And now we can enumerate those leaves in T minus. We have fixed two complete subtrees, T minus and T plus. In T minus, we denote the leaves by U1 to UN, and in T plus, we denote them by V1 to Vn. So we further consider a sequence of elements of actual tree automorphisms and a permutation, Sn. So then we can define the homomorphism of the boundary, denoted by this triple of T minus, T plus, and in the middle we have like the permutation and the tree automorphism, just by sending the cone associated to Vi, which lies in T plus, and it gets sent to the cone U sigma of I, which is in T minus, and it sends an element of the word of the form VIW by applying Fi to W, replacing V by U, and applying sigma to I. So let's consider, yeah, and like homomorphisms that arise in this way are called almost automorphisms. So denoted by A out TD. So let's consider an example. We have like this almost automorphism. We consider some word in the boundary of T plus. It starts with 2 and then 2, 2, and then here. We have an enumeration of the vertices. Here, this is V5. And then we add to it something infinite. This is W. And if we want to apply this almost automorphism, we first have to apply F5 to W. We have this F5. We replace V by U, and then we apply like the permutation part here to 5, so we get 8. Okay. So almost automorphisms can be multiplied easily, but only if under if like the right tree of the left element coincides with the left tree of the right element. In this case, they just cancel out, and you multiply like the remaining elements as you would do in the typical permutation Leibniz product. However, this is not always the case. Sometimes other trees are here. So before multiplying them, one then first has to do a refinement of this tree, which typically called expansion. So what that means is, well, one has here a tree and here a tree, and of course, like one can add carrots to the leaves of those three over and over until the trees have grown to the same tree. So here's an example. We have an almost automorphism. We have U3 and V1. They correspond to each other in the way that 1 is sent to 3. And then we expand those trees by hanging carrots below, like this U and V. So here we have hang a carrot, and here as well. So this way we like expand the trees, but also we have to do something with the elements. Now before we had here F1. F1 was responsible for V1. And now we split F1 into its states and put them like below, put them below this vertex here. Then we have F11, F12, and F13. So in this case, we have like F12 has to apply to this vertex here. And also there's like an obvious adjustment to the permutation part that we have to do. But this is actually the crucial point where self-similarity comes into play. In general, after this kind of expansion, there is no reason to believe that F11 and F12 will lie in the same group where F comes from. But if we assume self-similarity, then F12 by definition will lie in the same group where these F's come from. So this is why, so if we want to multiply elements, and let's say Fi and Hi come from some given group, so here they still are in the same group, but if one first expands them and then multiplies them, then the states should better lie in the given group. This is why the self-similarity condition arises in the definition of Röver-Necker-Schevich groups. It is just the group of those almost automorphisms where these three automorphisms come from a given group. So this is denoted by VDG. So VD is typically the notation for the Pigman-Thompson group. This is why the notation is chosen. So in the case where G is the trivial group, this is just the classical Thompson group VD. Right. So self-similarity condition guarantees that it is a group that we have already discussed. And then let's collect some facts about those groups. So Röver-Necker-Schevich showed that, first of all, VDG is generated in somehow in the obvious way. Like one has the G part and the Thompson part, like, and this generates the whole group. This what makes it interesting for us is that the commutator subgroup is simple. The group itself might not be simple. However, it's not far away. So if the group that we put in is perfect, for example, then VDG is virtually simple, since the abelianization of this group is a quotient of the abelianization of G. So it's somehow VDG is not far away to be simple already. It's virtually simple if G is, let's say, has finite abelianization. So, and what we will need is that abelianization of VDG is given quite explicit relations. So the relations are, we consider a finite generating set of the group G. We split each generator into its Riesz decomposition, and then S the image of S and the abelianization has to coincide with the sum of its states. Yeah. Okay. Now this Röver-Necker-Schevich group tends to have very good finiteness properties. So in the case of the trivial group, there's a well-known result that Thompson's group VD is of type F infinity. Scott proved that, a bit of different language, that finite presentation is inherited from G to VDG. And then Skipper, Witzel, Zaremsky showed that this is also the case for every Fn. Although the crucial point of the paper was not the positive finiteness properties. This might have been even known at that time, but they like wrote it up. The crucial point is that they also found a way to translate negative finiteness properties of G to the Röver-Necker-Schevich group, at least under certain circumstances. So we were very surprised that like the corresponding results for homological finiteness properties did not appear in the literature so far. Although I don't want to lie to you, there is no creativity in this proposition. So it's just that despite of the 1,000 variation of Thompson groups, like this specific statement did not appear yet. Yeah, we had to make a reference now for this. Now, the actual problem for Skipper, Witzel, and Ceramsky, and also for us, is that the finiteness properties of Röver and Kashevich group tend to be better than the finiteness properties of the group G. So this was already observed by Röver, who like plugged in the Grigorcze group, which is not even finally presented, and then what comes out of it is finally presented. So then, in fact, it is of type F infinity by results of Belk and Matucci. So the question is how to get negative finiteness properties. So the way to do it is to find quasi-retracts, since quasi-retracts give upper bounds on the finiteness properties. So just a reminder, for quasi-retracts we need coarse-Lipschitz maps. This is just a map between metric spaces where the distance can only, after applying f, can only increase in this affine manner. So homomorphisms, for example, are coarse-Lipschitz. So now a quasi-retract is such a Lipschitz map from x to y if there is also a Lipschitz map from y to x, such that by precomposing the given one, rho, with the one from y to x, then we have like bounded displacement map. Yeah. Okay. Now in the case of existence, y is called the quasi-retract of x, and rho is a quasi-retraction. Okay. Now the reason why we look at this quasi-retraction I already mentioned is that they give upper bounds on finiteness properties. If we have groups G and Q is a quasi-retract of G, then if G is of type Fn or Fpnr, then so is Q. Okay. So now what we need is to find some quasi-retract onto G. So we plug in a self-similar group with certain finiteness properties, if we realize G as a quasi-retract, then we are actually done modulo the fact that VDG is not yet simple. Okay, so this we also skip. I mean, there's a history already of how to do this. I mean, Skipper, Witzel, and Ceramsky made it, and also afterwards, Ceramsky and others had like certain technical assumptions on on what kind of technical properties give rise to existence of such a quasi-retract. So yeah, okay, let's skip this. Yeah, there is an evolution of making this weaker and weaker, the assumption now, and our point is that actually no assumption at all is needed. Although still some vocabulary is needed. So what the vocabulary that we need is persistent retractions. So we start with a self-similar group, and the persistent retraction is a retraction with a property that, let's call it R, with a property that after applying R to an element and R to the state of this element at some vertex, then it does not change. So this persists at the states of a given element. So this is a persistent retraction, and we have seen already an example of a persistent retraction, namely in the affine groups that we have seen, like projection to the linear part is a persistent retraction. Yeah, this is a reminder, but we still know it. Right. The point is that, right, this is what I just said. This canonical map to the linear part is a persistent retraction, and it is quite clear. The state of a state is a state, as we discussed already. If we have an element of this form, it is given by a linear part and affine part. We have seen like the state of this element is given by the same linear part, but so maybe the translation part changes. But still, since the linear part is the same, persistent retraction, this map is a persistent retraction, like obviously. Okay, now this is just a summary of what we have seen so far. Okay, there's just one tiny extra thing. So if we have a finitely generated subgroup of GL and Q, then we can like multiply all those denominators of entries of matrices let's say capital N. And then it will, Q will also be linear over Z 1 over N for an appropriate capital N. So and then in particular, after adding like this translation part to it, it will be a subgroup of Fn Z1 over N. And this is a self-similar group, which we have already seen. And moreover, like the canonical map is the persistent retraction. So this is a summary of everything that we have seen now. And now the point of persistent retraction is that it allows us to deduce the existence of quasi-retracts. But one has to be a bit careful. So we plug in a finitely generated self-similar group, which is G. And what we claim is that the corresponding Rubin-Akashevich group might not necessarily have G as a quasi-retract, but Q. So it would be good if we want to keep the finiteness properties of G to make sure that this quasi-retract will have the same finiteness properties of G. So this is like the next thing what we have to do. So the proof is a bit technical. Let's skip it. What was this? Ah, yeah, it's still the same. Okay. Okay, this is what we have seen. Okay, now what is the remaining problem? The remaining problem now is that first, this group might not be simple. So the Röver-Nekashevich group. So here we have a finitely generated linear group. We know that by adding like this, the affine part to it might make it self-similar, have Q as a quasi-retract, but there are still two problems. First of all, this might not be virtually simple, and second, the finiteness properties of this group might be worse than those of Q. Yeah, like if Q is the trivial group, then this is not even finitely generated. So these two problems we still have to face. But yeah, we know explicitly what the abelianization of the Röver-Nekashevich group is. So we will use this information. And actually, a solution of this simplicity thing already appears in a paper of Zaremsky. There is he has a trick to do this, but only applies it for Boone-Higman type questions. But actually, it matches very well. This technique matches very well with our persistence retracts. So what he does is like he has some self-similar representations. Elements G are given like in this rest decomposition matter. And then what he does is he's doubling the action. So he's repeating this decomposition inside the state m times. The rooted part is also repeated m times. And then what he shows is, actually now an easy observation when one, first of all, one has to show that this is actually a homomorphism and this is injective. But this is rather clear. And also it is, when one writes it down, what the abelianization is, it turns out that there are only finitely many m's where this thing gives rise to a Röver-Nekashevich group with infinite abelianization. So the point is now that G has this other self-similar representation with let's say simple Röver-Nekashevich group, and now our thing can be combined with now his tree can be combined with persistent retracts to give rise to self-similar groups that still have the persistent retracts. But now the extra property that the corresponding Röver-Nekashevich group is virtually simple. So now the only thing that remains is like to the finiteness properties. So I just state what the problem is. The problem is that this finiteness properties here can be worse than that of those. So the remaining step is like to find a way of, we call it Baumschlag solitarization of linear groups. Yeah, the point is that Baumschlag in general, this might have worse finiteness properties than G, but sometimes it is very good. Baumschlag solitaire groups are of this kind, and the finiteness properties are good. So the remaining step would be like to Baumschlag solitarize linear groups, and then everything is done. So I think I have to stop here. Done.
said that characteristic was the big obstruction generalized. Is that to say that the lemmas about rigid subrings or the Peano integers you also have corresponding?
Yes. Yes, that's exactly the case. So actually, what is needed for this is that if you have a ring, it should have a principal ideal of finite index. So this is what is needed. Yeah. Yeah. Ah. Okay. Okay. Yeah. Essentially, it's a rather easy observation. The point is we have a linear group and we add. It might have a center. It might contain diagonal matrices with constant entries. But first, we ensure that it doesn't. So just embed it in another way into a linear group such that it has trivial intersection with the constant diagonals. So then the second point is then add a specific diagonal matrix to it. Namely, if we have like coefficients in Z1 over n, just add n. So then after adding n, then the affine part is Z1 over n, Z1 over n and those, this thing. Then the group only generated by the diagonal matrix and this Z1 over n part, it will be a high-dimensional analog of bound-struct solitar groups. It can be written as H and n extension over Zn, and so it has good finiteness properties. Now, after adding this group combined with a given linear group, will then have all of the needed properties. Then it's not so difficult to see, actually, to verify that all the properties are satisfied then. Yes. Yes, yes. Okay, so, all right. No, it's just perfect. If we have time, then sure. Yeah, okay, first we have to find appropriate generating sets. So the generating set that we consider is the generating set of the Thomson group V. Actually, it should be VD. And the remaining generating set we consider from Q and even the remaining part from the kernel of the retract. So we have the three types of generators now. And then we show that this retraction is in fact 1-0 Lipschitz. But a bit of annoying thing with respect to left calligraphs, because we have chosen left actions. Yeah, this is what I was a bit lying. Actually, one has to redo everything for right action to get here right calligraphs. But yeah, it is. So now then check the corresponding generators. If we, for example, okay, this is a slight simplification since we assume that the trees match here always. But if, for example, we add to it like the Thomson part, this generator of Thomson group, then the only thing that happens is that we add a permutation afterwards. So now this sigma and this tau, there will be just one permutation. And I did not tell you what the quasi-retract is. It is just you have this almost automorphism. You have some decomposition. It might not be unique. I mean, there are many triples defining the same element. But still, you just chose the first element in this tuple and apply the actual retraction onto it. So just R to G1, and then you prove that this is in fact 1 Lipschitz. For example, after adding the permutation, like you get an element of this form, and then like after applying R, you again obtain the same element as before. Yeah. Now one has to check that this is actually well defined. So this is where persistency comes in. It comes in at several parts. For well-definedness, one needs it since, as I said, there are several triples defining the same element. So one has to get sure via this persistency assumption that all of that for every representation of a given element, one obtain this quasi retract is always the same element. So this is where it comes in, and then after applying the Thompson type generator, then the same elements come out of it. And if you apply a generator of the remaining group, again assuming that the trees match, then yeah, you multiply this element with this element as you would do in a Vries product. Then you have like some permutation of the S elements, and the G elements stay here. So what the quasi retract does is it maps this element, it just applies the retract to this element here. So in this, you will then, if you do it, you will end up with applying the retract to the generator, and then you have the retract of the remaining elements, since R is also a homomorphism. But RS is either 1 if the generator is from the kernel part, or it lies in SQ again in Q, since the retract is the identity on Q. So actually that's it already. Yeah, sure.
I think you said that G wasn't necessarily a quasi retract.
Yes.
So is the identity not a persistent retraction?
The identity, you mean, is the identity from VDG to VDG? You mean like to the trivial group, or?
G to G. That's right. Maybe that's
I see. Just to G1. You just replace R. Yeah. Now I see what you mean. No. It will not be well defined.
So the answer is that the identity map may not be persistent.
Yes. Yeah. It will. Yeah. Okay.